Okay, let's unpack this. Today, we're doing a deep dive not into geopolitics, but into pure logistics and the terrifying 90-minute crisis that nearly shut down global trade.
And years before the Ever Given ever got stuck.
Exactly. We are focusing on the near drowning of the Emma Mærsk on February 1st, 2013.
And you really have to understand the scale of this ship. It was a Pioneer, an ultra-large container vessel, nearly 400 meters long.
So a monster.
A complete monster, capable of carrying over 14,000 containers. It was basically the physical embodiment of globalized efficiency.
And the location here is just as critical. We're in the Suez Canal.
Right. This isn't just some convenient shortcut. It's an indispensable global artery. I mean, any disruption there sends immediate shockwaves through the entire world economy.
So you've got all this risk concentrated in one narrow ditch.
That's the perfect way to put it. Our mission today is to really dig into the Danish Maritime Accident Investigation Board's findings on this, because this wasn't just a breakdown.
No, it was a race against time.
A race against time that exposed this whole chain of, technical, structural, and procedural weaknesses in these megaships.
And here's the thing that's just so mind-boggling, the thing we'll keep coming back to. This titan of the seas was nearly brought down by a handful of cheap, incorrectly installed plastic cable seals.
That's it. That's the core of this whole deep dive. The massive, powerful engineering of the hull was betrayed by the fragility of a single, inexpensive component.
So let's set the stage. The Emma Mærsk. It's all about scale and centralized power. It ran on one single, massive Watertight main engine.
We're talking over 80,000 kilowatts of power. It's enough to run a small city.
But there's a catch, right? A single main engine means
a single point of failure. And that vulnerability was about to be savagely exposed.
Okay, so what's the scene?
It's nighttime, about 9:34 p.m. local time. The ship is proceeding southbound through the canal in a convoy. Everything is routine. You've got a pilot and the master on the bridge.
And the stern thrusters are running.
Yep, in idling mode. Those are the small propellers on the side that help it steer in, tight channels. Everything seems normal.
For about 7 minutes.
For 7 minutes. At 9:41 p.m., the crisis just explodes. A fire alarm goes off, immediately followed by multiple bilge alarms.
So the engineers run down to the shaft tunnel expecting smoke.
And instead, they find a torrent of water.
What happened?
A mechanical catastrophe. The forward stern thruster had a total breakdown. The report says the flange neck, that's basically the housing where the propeller shaft enters the hull, it was torn completely off the tunnel weld.
Wow. So a giant hole just opened up in the ship.
Instantly. A massive hole, creating a severe, immediate flood in that compartment.
The engineers must have been scrambling.
Oh, absolutely. They sound the alarm, they activate the bilge pumps, but the water is just rising way too fast. They're basically fighting the entire Red Sea, coming through a hole the size of a small car.
And very quickly it becomes a level 10 emergency.
Within minutes. By 9:50 p.m., the water is at the threshold of the watertight door that separates the shaft tunnel from the main engine room.
The last line of defense.
The last line of defense. The master orders it closed. So, for a moment, the immediate danger is sealed off.
But he knows that's not enough. The threat of a total power loss it's imminent.
Right. And the chief engineer's instinct is, let's conserve power, hold our position. But the master, he makes this incredible high-stakes call.
What does he do?
He overrides the chief engineer's advice. He speeds the engine up to 60 RPM maneuvering speed. It's a huge risk.
He's flooring it.
He's flooring it. It was this desperate race against physics to shove this 400-meter ship into the only safe harbor nearby, the Suez Canal container terminal turning basin, before everything went dark.
Before they lost all power and steering.
Exactly.
You have to just pause and appreciate that decision. They're going at high speed in the narrowest, most critical choke point in global shipping, knowing their engine could die any second.
If they fail, they block the entire canal. I mean, the stress on that bridge must have been almost impossible to comprehend.
And unfortunately, that watertight door they closed, it proved to be, only a minor delay?
A very minor delay. The investigation found that this supposedly impenetrable barrier was, in fact, the next point of catastrophic failure.
And this is where it gets really fascinating, because the integrity of that wall, a bulkhead specifically designed to save the ship from flooding, was compromised.
Fundamentally compromised by a terrible design choice. About 15 minutes after the master slammed the throttles forward, at 10:05 p.m., the bulkhead fails.
It didn't just buckle or break.
No, it was breached at specific tiny weak points. 4 high-voltage cable penetration sealings. They just burst.
4 seals. That's chilling. So why did these seals, which are supposed to keep the wall watertight, why did they fail so dramatically?
It all comes down to cost and convenience versus, catastrophic necessity. The seals use these plastic or elastomer stay plates.
And those are the things that let the cable bundles pass through the steel wall.
Exactly. The problem was the manufacturer rated those plastic plates for a maximum hydrostatic pressure of 1.0 bar.
Okay, so what was the actual pressure they were facing from the floodwater?
The water in the flooded shaft tunnel was about 9 meters deep. That depth creates a pressure of approximately 0.9 bar.
Oh, wow. So it was right at the seal's breaking point.
Right at the limit. There was essentially zero margin for error.
Wait a second. Someone signed off on using cheaper plastic parts in the one place they knew catastrophic flooding could happen. Was that just negligence or what?
The investigation showed it was a systemic flaw. The plastic plates were cheaper, they were faster to install, and the main focus during their selection was on fire resistance.
Not water pressure?
Not water pressure resistance. They treated it like a firewall and completely ignored the fact that it was also a flood barrier.
That is just incredible. So what should they have used?
Metal stay plates, the kind that are actually designed for a proper watertight bulkhead. Those are tested to withstand 5.5 bar.
Ever 5 times the pressure.
Over 5 times. So they used the wrong material because it was easier, and the simple physics of 9 meters of water just pushed the cheap plastic past its limit.
And the cascade effect of that failure must have been devastating.
It was. The investigation estimates a total of 14,000 cubic meters of seawater poured into the engine room.
14,000. I mean, what is that in real terms? That's enough water to fill, what, 6 Olympic-sized swimming pools?
Something like that, just pouring into a live working engine room. That volume of water immediately compromised switchboards, electrical components, everything.
And at 10:55 p.m., the inevitable happens.
The main engine stops. It loses all its support systems, especially the cooling water pumps. And just like that, this 400-meter Titan is dead in the water, blocking the most vital trade channel on Earth.
And while all this is happening, the crew is trying to cope.
Yeah, and the report makes a specific point about this. The officers and crew were constantly bombarded by the sound of countless alarms.
So the systems meant to help them were actually hurting them.
Exactly. The crew said it just added to their cognitive burden. It became this incredible distraction, impeding their ability to actually get an overview and concentrate.
That's such a modern kind of failure, isn't it? Data overload actually paralyzing action. It wasn't a lack of information, it was the sheer noise of it all.
Right.
Okay, so we've got the initial thruster failure, then the structural failure of the bulkhead. But the problems didn't stop there. This was like a 3-layer failure.
That's a great way to put it. The next layer was the failure of the functional barriers, the emergency systems designed to mitigate this exact scenario.
You mean the bilge system?
Primarily the bilge system, yeah.
It sounds like they had pumps, but they were useless. Why would a billion-dollar ship have a bilge system that couldn't handle a flood?
Well, the main issue was a missing isolation valve. The engine room bilge system couldn't isolate the flooded shaft tunnel from the rest of the system.
So when they closed that watertight door,
the entire bilge line running through that area got pressurized from the massive volume of water now trapped there. This meant the main bilge pump couldn't clear the water still seeping into the engine room because it was fighting the full pressure from the next compartment over.
Their main defense was just neutralized by a design flaw.
Completely neutralized. They had to rely on the emergency backup, the big one.
The emergency bilge suction pump?
Which was enormous, rated for 3,200 cubic meters per hour. But it had 2 critical weaknesses.
Of course it did.
First, its intake was only 50 millimeters, 2 inches above the tank top. So as the ship rolled or the water level dropped even slightly, it sucked air and the flow was severely restricted.
And the second weakness?
It was trying to discharge water through the central cooling system pipework, which created back pressure and throttled its own capacity.
And this critical pump is tied to one of the most just nail-biting human moments of the whole crisis.
Absolutely. An engineer goes to open the emergency bilge suction valve by hand. This is their last hope. And a tiny steel pin in the handwheel gear breaks.
You're kidding me.
The handwheel just spins uselessly. So this engineer has to crawl under the floor plates into knee-deep live electrical seawater and manually open the valve with a wrench.
That's heroic. It's an immediate adaptive response to a tiny fragility that nearly compromised their last chance.
Incredible bravery.
Let's go back to the very, very beginning. The root cause of the thruster breaking in the first place. What made that flange neck tear off?
We're back to the design layer. The investigation found the propeller blades broke because of fatigue cracking. The fatigue was linked to an unfavorable design detail. The root radius of the original blades was too small.
What does that mean?
It was specified to be 25 millimeters, but it was actually only 10 to 12.5 millimeters.
So it's like finding a tiny pre-existing structural weakness in a load-bearing column.
Precisely. That sharp notch created a high-stress concentration, which led to blade fatigue, failure, and the catastrophic water ingress. It's truly incredible how an error of mere millimeters in manufacturing tolerance led to a 14,000 cubic meter flood.
But despite this just overwhelming chain of failures, the crew somehow managed to avert a total disaster.
Their actions were the ultimate mitigating factor. The crew's quick, adaptive actions, like the engineer opening that valve by hand, or another crew member who jammed a wooden bar and wedges into a leaking cable penetration in a cargo hold, were crucial.
And the master's focus never wavered. His priority was always getting the ship into that turning basin. That one decision saved the entire canal.
And that successful move bought time for external support. The Suez Canal Authority's response was instrumental. They deployed 4 tugs immediately and, crucially, they managed the convoy traffic.
I saw a note about an LNG tanker.
Yes, they stopped a very large LNG tanker that was steaming right behind them. They prevented what would have been a catastrophic and possibly explosive collision in that tight channel.
So if we pull all this together, the near drowning was averted by human adaptation and external support.
Despite failures in all 3 layers. The design with the weak thruster, the structural barriers with the cheap cable seals, and the functional barriers like the flawed bilge system.
It seems like the main lesson is that you can't rely on a single craftsman or a single component when the stakes are this high.
Exactly.
So what were the long-term industry changes that came out of this? Because this had to be a global mandate for change.
Oh, the implications were huge. The thruster manufacturer, Rolls-Royce, they immediately changed the blade design and invested heavily in computational fluid dynamics to better understand those stress loads.
And what about the ship owner?
Maersk Line prohibited using the stern thrusters on that entire class of ship until the blades were replaced and the tunnel structure was reinforced.
And the regulators, the classification societies, they had to step in on those seals?
Absolutely. The American Bureau of Shipping, ABS, they significantly tightened the rules. They now require ship equipment lists to specify the exact manufacturer and type of sealing device.
To make sure the right pressure-rated material is being used.
They essentially closed the regulatory loophole that let cheap plastic seals get substituted for metal ones in a watertight wall.
So when you take a step back from this whole story, what should you, our listener, take away from this?
Well, it's a deep dive into how this shift toward these ultra-large vessels concentrates enormous economic risk into single choke points like Suez. And the crisis hinged on components as small as a plastic cable seal, a tiny broken steel pin, and a design error of 15 millimeters.
It's incredible. If the master, the engineers, or the Suez Canal Authority had been even slightly slower, the resulting blockage from a fully flooded ship could have dwarfed the ever-given disruption.
So the final provocative thought is this. How truly resilient are our global supply chains when the world's economy hangs on the hydrostatic integrity of an elastomer seal?
It reminds us that often the most catastrophic failures aren't prevented by high technology.
Not at all. They're prevented by the sharp eyes and quick adaptive thinking of the crew fighting physics in a flooded engine room. It just proves that in mega logistics, the weakest link is always the most important one.
A truly sobering lesson in the reality of global trade. Thanks for diving deep with us today.